Hi, future GISPs. I'm going to teach you everything that I learned to easily pass the GISP exam so that you don't have to spend years reading textbooks, getting degrees, paying for prep courses, and searching the internet for information like I did. In this video, I'm going to teach you everything I learned about the representation of discrete features and continuous phenomena in GIS. Representation of discrete features and continuous phenomena in GIS is the second section under the Conceptual Foundations category of the GISCI Geospatial Core Technical Exam list of knowledge categories. Let's get started with section 102, representation of discrete features and continuous phenomena in GIS. A GIS dataset. A GIS dataset must have features, attributes, and spatial information. Discrete data. Discrete data only occurs at specific locations and has well-defined boundaries. Discrete data is usually in vector format. Discrete data is also called categorical or discontinuous data. Features or areas in a discrete dataset can be assigned one of a predetermined set of categories. Continuous data. In a continuous dataset, each location is a measure of something. Continuous datasets are often in raster format. Examples of continuous datasets include elevation and temperature. Continuous datasets can contain fuzzy data, where the categorical membership of areas is not certain. There are two types of geospatial datasets, vectors and rasters. Understanding the differences between these two types of geospatial data models is one of the most fundamental concepts in the field of GIS. The vector data model. The vector data model is a coordinate-based model that represents features with points, lines, and polygons. The vector model stores geospatial features as entities. Let's take a look at some of the advantages of the vector data model over the raster model. Vectors are more efficient than rasters for storage. They have smaller file sizes because they don't require values to be stored for every location like rasters do. With vector datasets, accuracy is only limited by the measurement process. You don't have to increase the resolution and increase the size of the whole file to record a point at a larger scale. Vector files can support topology and record relationships between features. Vectors support interactive retrieval, which means users can query data to find a specific feature. Vector layers can be overlaid for making maps with multiple datasets. Generalization is possible with vectors. Generalization means lines can be represented with fewer points as the dataset is viewed at smaller scales. Vectors can represent smooth curves and boundaries, whereas rasters have a stair-step shaped boundary. A popular saying in GIS literature is, vectors seem more correcter. This means the vector data model is more capable of storing more highly accurate data than the raster model. Those were the advantages of storing geospatial data in a vector format. Now let's take a look at the disadvantages of storing data in a vector format. Vector disadvantages. Vectors are more complex datasets to deal with from a programming perspective. Vectors are less intuitively understood. This means it's easier to explain to an untrained person how a raster file works than it is to explain how a vector file works. Overlaying multiple vector files is computationally intensive. It takes more resources for a computer to display multiple vector files at once than a single raster file. Vector data is not easily programmed into a computer. Vectors are not good at representing variable coverages, such as temperature or elevation. Vector datasets are made up of points that form point, line, and polygon features. Now that we've covered some of the advantages and disadvantages of the vector geospatial data model, let's take a look at the key components of vector data creation and analysis. Key components in vector data creation and analysis are points, lines, and polygons. Points. A point is a coordinate location described by x, y, and sometimes z values. X defines the longitude, y defines the latitude, and z defines elevation. Lines. A line is an ordered set of connected points. Line features begin and end at nodes. Vertices define the shape of the line in between nodes. Polygons. A polygon is a set of vertices on a planar surface that begin and end at the same point. A polygon is also known as a bounded area. An intersection. An intersection is a point common to multiple lines or multiple surfaces. A node. A node is a point at which line features end, intersect, or branch. Nodes are central or connecting points. Pseudonodes. A pseudonode is a node at the end of a line feature that connects to a node of only one other feature. A pseudonode makes it appear as though two separate features are one. A pseudonode may indicate where two features can be merged. A dangling node. A dangling node is a point at the end of a line with no connections. An edge. An edge is a line that forms a boundary between two features. A curve. A curve is a line that is defined mathematically rather than by a series of connected vertices. A curve may also be called a parametric curve or a Bezier curve. A centroid. A centroid is the central location of a polygon. A centroid can be located outside of the polygon. Area. Area is the amount of space a polygon contains. Perimeter. Perimeter is the total measure of the length of the outside of a polygon. Those were the key components in vector data creation and analysis. Now let's explore the raster data model. A raster. A raster dataset is a representation of the world as a surface divided into a regular grid of cells. Rasters are useful for storing data that varies continuously, such as aerial photography, satellite imagery, pollution concentrations, or elevation. Rasters can have single or multiple bands. Bands are values per cell. Let's take a look at some of the advantages the raster data model has over the vector data model. The raster data model is easy to understand. It's easy to explain to an untrained person what a raster dataset is because most people are familiar with digital pictures or videos, which are forms of raster datasets. Rasters are good at representing continuous, highly variable surfaces, such as the terrain of the surface of the Earth. Rasters are easy to input into and output out of computer programs. Rasters are easy for programmers to work with. It's easier to program analytical operations such as autocorrelation, interpolation, and filtering with rasters as opposed to vectors. Map algebra can be performed on raster datasets. Rasters are easily programmed into an array memory structure. Rasters work well for representing scanned data or remotely sensed data. Rasters are easy to display on a screen or print as an image. A popular saying in GIS literature is, "Rasters are faster." Rasters are faster means learning how the raster data model works and how to program raster datasets is a faster process than learning how the vector data model works and how to program vector datasets. Now let's take a look at some of the disadvantages of the raster data model over the vector data model. Rasters have larger file sizes than vectors because they have to store values for the whole area that the raster file covers, even if there is no meaningful data in some areas. Rasters can be compressed to reduce file size, but compression techniques are not efficient with variable data. Compression techniques are only efficient when large areas with the same values are present. Using large cells and rasters will reduce file size, but could potentially cause information loss. Rasters are poor at representing points, lines, and polygons. Every cell in a raster dataset can only be owned by one feature. Raster datasets must include redundant and missing data. The mixed cell problem. The mixed cell problem occurs when multiple values, or features, exist in an area covered by only one cell. There are several solutions to the mixed cell problem, all of which result in information loss or increased file size. Those were the advantages and disadvantages of using the raster data model to store geospatial data. Now let's take a look at some of the components of the raster data model. Types of raster datasets used in GIS include remotely sensed imagery, such as photography and LiDAR, surfaces, scanned maps, and classified images. A classified image is an image that consists of categorizations of land cover. Rasters can contain a discrete or continuous range of values. Discrete rasters. In discrete raster datasets, cells are limited to predetermined categorical values. These are usually integer values. Continuous rasters. In a continuous raster dataset, cells have gradually changing values. Continuous raster datasets can have floating point values. A pixel. A pixel is the smallest piece of resolvable information in a raster or picture. Pixels are called cells in raster data models. Cells are connected to tables with indices. Attributes, or bands of data, are stored in tables connected to cells with indices. A popular saying in GIS literature is, "A cell is always a pixel, but a pixel is not always a cell." This means pictures are raster datasets, but raster datasets do not have to be pictures. Bit depth. More bits means the dataset has a greater range of data and can represent finer gradations of color. 8 bits allow 256 different values. 16 bits allow 65,000 different values. Elevation rasters usually require 16 bits. A higher bit depth allows greater detail at the cost of a larger file size. A lower bit depth provides a lower range of data and reduces the file size. A digital elevation model, or DEM. A digital elevation model is a data model used to process, store, analyze, and display elevation data. A digital elevation model is traditionally a digital terrain model. A digital terrain model, or DTM. A digital terrain model is a type of DEM that aims to represent an idealized land surface, where surface objects such as buildings and trees have been digitally removed. A digital surface model, or DSM. A digital surface model is a type of DEM that represents a maximum elevation within a grid cell. A digital surface model records the tops of buildings, trees, and other objects. A mixed pixel. A mixed pixel is a condition whereby more than one category of object is present within a single grid cell. Possible solutions to the mixed pixel problem are: you could rank the categories and assign the more important category. You could use a fuzzy classification. You could assign a mixed category. Or you could reduce the pixel cell size. All of these solutions to the mixed pixel problem will result in data loss or increased file size. Those were some of the components of a raster data model that appear on the exam and in GIS literature. Here are a couple of concepts that apply to both raster and vector data models. Extent. The extent is the area or distance in real space over which some geographic entity exists. In cartography and GIS, the extent of a representation is the size of the real space being represented. Resolution. Resolution is the degree of detail to which a phenomenon is detected or represented. GIS data are stored and rendered at some degree of representation resolution. In rasters, resolution is defined as the pixel size. In vectors, resolution is the smallest distance that can be detected between two features. Now you know everything that I learned about the representation of discrete features and continuous phenomena. Don't forget to thumbs up and subscribe to my channel so I can keep helping people pass the GISP exam and achieve the rewarding careers in GIS that they deserve. You can also find everything I learned to pass the GISP exam in my book, The Ultimate GISP Exam Study Guide, available on Amazon. My study guide is an easily understandable, comprehensive, graphical, all-in-one resource for passing the exam. You can find the link to my study guide in the description below. Thanks for joining me, and congratulations in advance on passing the GISP exam.